Okay, so hopefully this is the last part. If this takes more than 15 minutes, we've got some issues. Okay, so it says here, explain the process that occurs to form ionic and covalent bonds using diagrams if necessary. So there's a bit of space for words, there's a bit of space for um, diagrams. So I'll do the diagrams first, just to help explain it. So if we have two substances, let's pick something super simple. So let's pick sodium and chlorine. Um, Remembering that it's the outer shell electrons that are the things that are interacting with each other, I'm going to draw the Lewis dot structures for each of these. I'm going to draw the sodium with the cross, and I'm going to draw the chlorine with the dots. So knowing that chlorine is in group 7 or 17, I know that it has 7 valence electrons. So we have 1, 2, 3, 4, 5, 6, 7. You can see that sodium here has 1 electron in its outer shell, and ideally it would have the previous number. So it doesn't want 1; it would rather 8. Now there's not you can't. It's very difficult to put 7 more in this shell. So what we're going to do is we're just going to take that 1 away, which will give it the previous levels 8 completely filled. So what happens here is the sodium wants to get rid of that electron. The chlorine really wants 1 extra electron, so we're going to do this here. We're going to transfer it over. So sodium is going to end up like this. Now, what you could do if you really wanted was you could have the next shell written there, but I'm going to leave it like this. I'm going to put a little plus above it. And we have our chlorine, which is going to have all 7 original plus the cross from the cross electron from the sodium. And now we have our negative charge here. It's the interaction, the positive and negative attraction between these two that has ionic bonds, or makes ionic bonding a thing. So we have a positive charge and a negative charge, and they attract each other. Cool. So we'll try and explain that in words. When two, or actually, let's make it a bit clearer. When a metal and non-metal react, the non-metal takes electrons from the metal, making it an anion, which remember is a negative ion, and the metal atom turns into a cation, which is a positive. The attraction between positive and negative ions gives ionic bonding. So the bond between them is between a positive and negative charge. And that's pretty much it for ionic. Now, covalent is when you have two chemical species that are both non-metals, and they're going to share instead. So let's try something relatively simple. Let's do fluorine and fluorine. So we're going to attach. Actually, let's go fluorine and chlorine. So we're going to attach these two together. Now, fluorine is in the same group as chlorine. So they're both going to have 1, 2, 3, 4, 5, 6, 7. And you know what? Because I know they're going to join together, I'm going to draw it a little bit differently. I'm going to go 1, 2, 3, 4, 5, 6, 7. Because I want to put the unpaired one, the one that I know is going to bond with the other. I'm going to put that closer in between the fluorine and chlorine. So 1, 2, 3, 4, 5, 6, 7 outer electrons with the chlorine. And again, I'm putting that unpaired one on the same side as the fluorine, so that because I know they're going to interact with each other. Chlorine wants 8 in its outer shell. Fluorine also wants 8 in its outer shell. So what they're going to do is they're going to take a bit of ownership in their unpaired ones each. They're going to share them so that they have almost like a sort of a pseudo full outer shell. So I'm going to bring them closer together. You're going to have our chlorine and our fluorine. Nice and, oops, it's just an F. And I'm going to put my 1, 2, 3, 4, 5, 6, 7. And then I'm going to put my 1, 2, 3, 4, 5, 6, 7. So if we would, I'll put one on top of the other here. So that there is the electrons that each of them are sharing that helps them sort of fill up their outer shell. So if you were to cover up the fluorine, you'd see that chlorine has a full outer shell. If we do the same for the chlorine, cover that up, the fluorine looks like it has a full outer shell. So each of them sort of have a part share in that full outer shell. This here is the covalent bond, and if we wanted to, we could rewrite this and replace the electrons that I've circled with a line and have our extra electrons just floating around just like that. So the difference here is that they're both nonmetals and they're sharing their electrons instead of one taking them, the other one receiving them. So covalent occurs between nonmetals where they share electrons to help fill both their outer shells. Instead of one taking and the other losing. So it's not that. So they bond through, they bond through the shared, that is not even, they bond through the shared electrons. And that's pretty much it. So these diagrams here help show one has taken the electron and the other one's lost it. And this one here, they're sharing them instead. Okay, so 17. I think that's the last question. Oh, 18. I've got a bit to go. So 17. Draw the Lewis dot structures for potassium, hydrogen, and fluorine. So potassium is K, hydrogen is H, and fluorine is F. Potassium is in the first shell, so we're going to make a single dot there. Hydrogen is there, and fluorine has our 1, 2, 3, 4, 5, 6, 7, like we've shown before. It says here, draw the Lewis dot structures after potassium and fluorine have combined, explaining whether they've formed an ionic or covalent bond. So knowing that potassium is on the left-hand side of the periodic table, it therefore is a metal. When it's a metal, it's going to interact with a non-metal and form an ionic bond. So our potassium, I'll redraw it actually up here as a dot just for fun. So we have our K started like this. Now fluorine started like this. They're going to end up as our K plus, losing that electron, and our fluorine is going to have stolen that electron. So, and it's going to become a negative charge. So it's going to be ionic as metal plus non-metal. Essentially, the fluorine really wants that electron, and the potassium doesn't really want it that much. So the fluorine is going to essentially pull it away too strongly and become a negative ion. The potassium is going to become positive, and we end up with a ionic bond. So you want to try and explain that as best you can. Similar for hydrogen and fluorine, we have hydrogen. I'm going to draw it like that. We have our fluorine. The difference here is they're both non-metals, which means hydrogen is trying to fill its outer shell to get to 2, Remember, hydrogen is in the first, has its first shell, that electron's in the first shell, and it only needs 2. Fluorine needs 1 electron here. It's similar-ish to potassium, except that hydrogen does want to hold on to that electron, and it wants to gain another one reasonably well. So that means instead of fluorine stealing that one, they're actually going to have a nice little even share. It's not really very even, but it's even enough to be called covalent. And we're going to end up with this happening here. So the key bit here is we have 2 nonmetals. Each of them want the electron enough that they're not going to, fluorine or hydrogen isn't going to steal it completely. They're just going to have to share because they both want that electron enough. So you can try and explain that. Okay, and last one, see if we can fit it in. An unknown compound is either covalent or ionically bonded. We don't really know which one it is. Its properties are listed in the table below. Now it says explain, referencing each property, so that would be each one of these, whether the substance is an ionic or covalent compound. Now, this was something we didn't spend heaps of time on, but we did look through the periodic table, the interactive one online, and we made up some substances and we made some ionic ones and some covalent ones. Remember, to make ionic, we need metals and non-metals. Covalent, we had 2 or more non-metals. And we had the substances, we had to look at their appearance, their melting points, solubilities and conductivity in water, stuff like that. And hopefully, or we did come up with a few things that were quite common. For example, ionic substances have high melting points. Oops. So high melting points. We're talking, somewhere, greater than 400 degrees Celsius. So some of them are, in the hundreds, or, as in 500, 600, 700. They dissolve in water. Actually, dissolve in water. So some dissolve in water, some don't. So variable solubility. So in other words, if their melting points, if a substance's melting point is low, it's evidence towards being covalent. If its boiling point or melting point is high, then it suggests ionic. But remember, it's always a suggestion. It's never, a smoking gun. It's never, this means it's definitely this or one way or the other. So the other thing is, if it does dissolve, if dissolved, ionic conducts electricity. Oops. And that's pretty much it. Covalent has low melting points normally. And we're talking, negative 100 degrees Celsius all the way up to maybe 200 or so. They also have variable solubility, but if they do dissolve, they do not conduct electricity. So for this question here, you should be looking at each of the points and saying appearance: a white, odorless, a white, odorless, crystalline, or powdery solid. That doesn't tell us much, but it does tell us that it is a solid at room temperature, and that is leaning. So crystallized substances are leaning towards ionic, but covalent also can be. For example, sugar is a covalent substance, and it's obviously a white, odorless, crystalline substance. Now, melting point of 186, medium, so it's not too high or low. So I would say this is inconclusive, but I can't even spell inconclusive. Inconclusive, but leaning towards maybe low. So maybe leaning towards covalent. and the time is about to go off. So I guess